So in this module, we're going to begin talking about applications of calculus. And the first application we're going to look at is from section 2.6, and we call this linearization and marginals. All right, and so this picture kind of describes what it is that we're trying to do. So let's say that we have this graph here, f of x, and we know what the value is of f of x at some value x. All right, so at x, the graph f of x has a y coordinate that's equal to f of x. Okay, so let's say that what we want to do is we want to estimate what is the value of f of x at some future value of x, which we're going to call x plus delta x. All right, how would we figure that out if we didn't know what the function was at that point? So one thing we can do is we can do what's called a linearization or a linear approximation to that point by using the first derivative. So let's say that at x, instead of going all the way to where f of x would be at x plus delta x, what we do is we draw a tangent line to the graph at x. Okay? And when we do that, we can figure out where the tangent line would end up when x is equal to x plus delta x by saying that the change in y would be f prime of x times delta x. So if you remember, f prime of x is going to be dy dx, so the change in y over the change in x. And then if I multiply that by delta x, I end up getting a change in y. So what we can say is that f of x plus delta x is approximately equal to f of x plus f prime of x times delta x. All right, so we use the approximately equals to because the actual graph is up here, but the approximation using the linearization is down here. So if we don't have information about what the graph looks like past to the right of x, then if we do know what its derivative is at x and we know how far over we want to go delta x, then this here gives us a way to approximate the function value at x plus delta x. Okay, so let's look at a couple examples of where this might be useful. Let's say that we have f of x is equal to x squared, and we want to estimate f of x at x is equal to 2.1 using f of 2 and delta x is equal to 0.1. So if we were to graph something like this, we would get a parabola. So if I just look at it from this side, and this is at 2, then if I want to know what it is at 2.1, using a linear approximation, what I can do is I can draw a tangent line at 2 and try to figure out what is the y value of this and use that to approximate what the actual y value is over here. And again, this assumes that we don't have information about what f of x is after x is equal to 2 for some reason. All right, so what we can do is we can say that f of x plus delta x is equal to f of x plus f prime of x times delta x. All right, and x in this case is going to be 2 because they give us we're estimating f of x using f of 2. So I can say that this is f of 2 plus 0.1, and this is equal to f of x, and x is 2, plus f prime at 2 times 0.1. All right, so this is saying that if I want to approximate, put squiggly lines here to say we're approximating what the function is here, I can say that the function is going to be what it is right here, which is f of 2, plus this extra term right here, which is f prime of 2 times delta x, which in this case is going to be 0.1. So then I can say f of 2.1 is approximately equal to f of 2 plus f prime of 2 times 0.1. All right, so I still need to figure out what f prime of 2 is. So I'll say that since f of x is equal to x squared, if if I use the power rule that says f prime of x is equal to 2x, so f prime of 2 is going to be equal to 2 times 2, which is 4. So I can say f of 2.1 is approximately f of 2, and f of 2, since f of x is x squared, is 2 squared, plus f prime of 2, which is 4, times 0.1. So this is approximately equal to 4 plus 0.4, which is 4.4. So f of 2.1 is approximately 4.4. All right, so the application for this class that's most important in understanding linearization and marginals is what's called marginal cost, revenue, and profit. And here we have a graph where x is a number of units produced and C of x is a cost of producing x units. And let's say that we know what the cost is of producing exactly x units. All right, so we're here at x, and that cost is C of x. And what we want to do is we want to figure out what is the cost of producing x plus 1 units. So we want to figure out what this is right here. So if we don't have any information about what happens after x units, we can use a linear approximation. So we draw this tangent line here, and this tangent line will say gets up to a y value that is approximately equal to C of x plus 1. And what we learned before is at this distance right here, this is going to be C prime of x times delta x. But in this case, our delta x is equal to 1. So this becomes 1, so this is just C prime of x. So if I want to write the expression C of x plus 1 is approximately C of x plus C prime of x times delta x, I can say that the cost of producing x plus 1 units is approximately equal to C of x plus C prime of x, since this goes to 1. All right, so one thing we can do from this is we can get C prime of x by itself, so we can say C of x plus 1 minus C of x is approximately equal to C prime of x. So this right here, C of x plus 1 minus C of x, this is the cost of producing the x plus first unit. All right, because C of x plus 1 is the cost of producing x plus 1 units, or the approximate cost in this case. C of x is a cost of producing x units, so the cost of producing the x plus first unit is going to be this difference here, which we can approximate by the derivative of the cost function, and this is what we call the marginal cost. All right, so the same idea works if we have a revenue function or a profit function. In those cases, I might write r of x plus 1 is approximately equal to r of x plus r prime of x times delta x equals 1, so we don't have to write that. And then I could say r of x plus 1 minus r of x is approximately equal to r prime of x. So this here we'll call the marginal revenue. And this here, say this is the revenue from the x plus first unit. Okay, and then we can do the similar thing for our profit function. We can say p of x plus 1 is approximately equal to p of x plus p prime of x. And so then p of x plus 1 minus p of x is approximately equal to p prime of x. This here is the profit from the x plus first unit. And this here is what we're going to call the marginal profit. Okay? So you'll see some examples of this on your My Math Lab, but the key formulas to remember for each of these is this here, this here, and this here.